Welcome to a session on placement processes. In this session, we'll see about the different placement algorithms. We'll start with the greedy algorithm. We'll see what are the disadvantages of greedy algorithm, and then we'll go to the simulated annealing. We'll see how the simulated annealing helps us to overcome the disadvantages of greedy algorithm, and finally we'll end up with the genetic algorithm. The greedy algorithm, as the name itself says, is greedy. It focuses on the best choice at every move. For example, when a move is made, the cost corresponding to that move is calculated. And if that move gives a placement with a low cost, that placement value is selected. If the move gives a placement with a higher cost than the previous one, this move is rejected. Right? So I'll explain this with the help of a diagram. Along the x-axis, I'll take x, and along the y-axis, I'll take y, which is a function of x. Okay, and this is the waveform that I have got. Right? So I'll name this. Here I have a minima, here I have a minima, and here I have a minima. I'll name this as A, this as B, and this as C. Right? Now, this operation reached this point A by accepting all the best moves, by accepting the costs which are lower than the previous iteration. After reaching the point A, it will not be able to climb up the hill because this algorithm is not designed to choose moves which give a high cost. So this operation gets stuck at A, right? Gets stuck at A. Now, is this desirable? No. We can call A and B as local minima, right? And C is the lowest of all. So what name can I give for C? I can call C as global minima. Okay. The aim of every algorithm is to reach the point C. But due to the greedy nature of this algorithm, it will not be able to go up to C. This is one main drawback of the greedy algorithm. How to overcome this? Simulated annealing is one method in which this can be overcome. This simulated annealing is derived from the process of annealing. Okay. So what is annealing? You go to a very high temperature, you cool it slowly, and when you do this, the material will solidify optimally into a state of minimum energy. This annealing process is used in many metallurgical processes. Simulated annealing has taken its idea from the process of annealing. How does the simulated annealing perform when compared to the greedy algorithm? The simulated annealing, it accepts all the good moves. Am I right? And all the bad moves, it accepts with a probability. It accepts with a probability. This is the difference between simulated annealing and the class of greedy algorithms. What are the steps involved in the simulated annealing process? We will start with a placement, right? And we'll keep the temperature at a very high value. The temperature is a controlling parameter as we had seen in the last slide. Now we cause a slight disturbance to the old placement. This placement, this is called a perturbing, right? So when you cause a small disturbance to the old placement, this makes the placement to become new, and we calculate the cost of the old placement and the new placement, right? If the cost of the new placement is less than that of the old placement, we accept the new placement as such. If the cost of the new placement is greater than that of the old placement, even now we accept it, but with a probability, right? So that is what is given here. This process will continue till you reach the freezing point. Yeah. So when you look at this one, you can see. Yeah, I'll take my pen again. Yeah. So these are the low moves. Lowest, the cost is getting reduced. All these good moves are unconditionally accepted. And then hill climbing. So this one is the cost is getting higher. Here also the cost is getting higher, and here also the cost is getting higher. So all these moves are accepted with a probability e power minus delta C by temperature. So all the good moves are accepted and all the bad moves are accepted with a probability. The probability is given by e power minus delta C by temperature. Okay, so this is the algorithm for the simulated annealing. You fix an initial temperature, you take an initial placement, you change the temperature, you keep on reducing the temperature, and then what is this perturbed place? You cause some initial changes to the placement, you calculate the cost for it. If the cost is less than 0, it is a good move. Am I right? If the cost is less than 0, it is a good move. So you accept the new placement as such. Else, if the cost is greater than 0, what should you do? If the cost is greater than 0, you should accept it with a probability. So this one is the bad move. Right? That bad move is accepted with a probability e power minus delta C by temperature. Is that clear? So as can be seen from this, when the temperature is initially high, almost all the moves will be accepted. Right? As you keep on reducing the temperature, this factor becomes large and the probability of accepting the moves also gets reduced. Okay. Yeah, we'll come to the next algorithm, which is the genetic algorithm. The genetic algorithm is completely analogous to nature. It chooses the biological concept of genetic engineering. Okay. Here we do not have a single solution, but we have a population of solutions, feasible solutions. Okay. And chromosome is an encoded form of a feasible solution. So two parent chromosomes are combined to form one or two child chromosomes. Okay. So this is one type of formation of the child. For example, in the first parent, this is the first parent and this is the second parent. How do I form the child? I take the first half up to a particular point, right here, and the second part is taken from the second child. Similarly, for the second child, I take the first part of the second parent, right? I think second parent, and then the second part of the first parent. Okay. So this is how you form a child in genetic algorithm. But the problem here is when this one is used to analyze traveling salesman problem and all, the problem might happen when the same place is coming twice in your chromosome, in your child. So the traveling salesman problem, we do not want the same city to get repeated again, right? So this is one major drawback of this particular algorithm, right? To overcome the disadvantage of the same city or same parameter getting repeated twice, we go for the next algorithm called the order crossover. I'll explain that using my next media. In this order crossover, we have been given with two parents, P1 and P2. We will be asked to generate two children, C1 and C2, and the condition which has been given is these segments should be retained. So I'll start with the first one. Okay. So I'll write the segment which has to be retained as such. A, B, C, D. Now we have to start writing from the second one. For example, I have B here, but B is already present in my segment.
So instead of B, I should write E. Okay. And when I come to C here, yeah, C is present, but C is already present here. So instead of C, I should write F. Okay. And the next thing is, I have X here. X is not coming anywhere here, so I'll write it as X, right? Similarly, I have Y here. Y is not getting repeated. Again, I have an X. X has come already in my segment. So instead, I'll copy O. H comes next. H is not present anywhere, so I can write H. This is how you form the children by using order crossover. So with this, we come to the end of the placement algorithms. We'll meet with some new contents in the coming week.